we will be playing science. We'll be playing science chemical. But damn it, I had so much time to start this and I no idea what was going to start. But yeah, today is my coffee day, which basically means that okay, the sound is swelling good. And yeah, which means that I can do science. I changed my mind. I decided I will not try to detox myself with coffee because it's not a toxin. It's actually good. So yeah, I'll just drink and do science, which is great. Today, topics of today's science stream. To already get you disappointed for the morning, I'm doing an 8 AM science stream, which is a great idea. It's a fantastic idea, in my opinion. Yeah. This is an 8 AM science stream, which, I mean, it's perfect, honestly. I listen, tell me, like, come on, everyone, let's be real, everyone wants to learn about chemical bonds from the quantum mechanical perspective at 8 AM. I mean, let's be real now. We all want that. And that's why I'm here. That's why I'm here. That's what I'm here for. So, the thing is, let me first tell you what the issue, what the problem is. Well, I am trying to write something, desktop projects, and what's it called? Molgen, yeah. I'm trying to write something with the epic name. Don't mind this. This is just. So we had fun. Last couple of streams. This is basically a parser that I thought I should just put on the single line because you know it. Don't mind that. But basically, I haven't even run this parser till the end actually. Oh shoot. Parse, which is right now it will work great with my Blender render in the background. Blender render, it doesn't matter. Point is, I got it. Haven't really got it, just download it from an online periodic table page. This, which is a lot of data about different. Is atoms even elements? I'm good with chemistry. Different elements. Then what I did is I parsed it. What does parsing mean? Parsing means just changing it so that it would be easier readable for my programs, for my usage, and that way I created the table, which has a lot of stuff here. As you can see, it looks different. It's the same data, but it looks different. Over here we have all strings, which basically means all text, which is not that optimal. Over here we have numbers, we have text, we have stuff like that, and we will also have over here where it says temp nothing, which means temporarily nothing. We will have an array of arrays, huge thing, fun, doesn't matter. The point is, I have all of this chemical data, and what I want to do with it is I want to write a program which could be used to simulate. Well, not simulate particles, only check how stable they are. Yeah, I feel like that's solid. That's a solid idea. It won't be easy. It will be actually upsettingly hard. That's why I'm making it in Python. Normally I would make it in C. That's funny because that was my name. Normally I would make it in C, but I'm making it in Python because that's how difficult it will be. It will be hard. It will be really hard. It will be a small thing, but a really difficult one to make. Because you see, chemical bonds are a mess. They are an absolute mess of information and stuff. Let me show you what I mean. In my, not paper, just document of things. The document of things that make it documents. If we go over to atoms, bonds, right? I think bonds are here. Nucleus, no. Properties, no. Bonds are not generalizable in any way or shape or form. They are just atomic, ionic, they are covalent, and they all are all about electrons, but some of them give away electrons, some of them share electrons, some of them, I don't know, take the electrons and... Actually, I think that's it. So yeah, the most important bit of an atom when it comes to bonding would be electrons. Ionic bonds basically mean that... Paint, if I may. Thank you. Yeah, I'm professional, as you can see, I use paint. So, ionic bonds basically look like this. We have an atom, and we have an atom. And this atom has a lot of electrons, right? It has whole... listen, I might completely fuck it up right now, so don't listen to a single word I say, but also do listen, because I like that. Let's see that we have two atoms. This one has 7 electrons. on its valence shell, important, which would mean that it would have 7 electrons on its second shell, on subshells 2 on the subshells S and 6 on the subshell D, if I'm not mistaken. Or 2, no wait, 2 of the subshell S and 6 on the subshell P, I think. Because I think it was SPDF. I'm pretty certain of. Yeah, doesn't matter. And this one would have 3. Then atoms for some reason really like number 8 and number 2. No idea why. I didn't manage to get this deep into it. But they like them numbers. And because of that, they might make a bond, which basically means that this atom would give one if its atoms over here and keep 2. And would you look at that? This atom right now has 2 electrons, which let me remind you, these are 2 separate numbers. I should mention. Look at that. It likes it because it has 8 electrons. That's very, very, very nice for this atom. Then another one, after it took this electron very violently, now has 8, which is also very nice. They also like that. And, you know, because of that, they are both very happy. And this one keeps these electrons. This one gave it away because now it has 2 and it likes that. But these still belong kind of to this atom. And because of that, these are kind of attracted to this. But at the same time, they are all attracted themselves. And just like that, we have a bond. They are bonded together. Great night. Nice, amazing, wonderful. I'm pretty certain that is ionic bonding. I'm decently certain. We can check. We can check the definition. Define ionic bonding. Damn, I'm a nerd. I'm such a nerd. So yeah, electrocovalent bond. Obviously, you have covalent, electrocovalent, formed from the electrostatic attraction between oppositely charged ions, chemical compound. When valence are transferred permanently to another atom, the atom that loses the electrons becomes positively charged. So then let me just paint this. Yeah. So then this would be a cation. Cation it's not calcium, it's cation. And this would be an onion. Negative onions. I have to remember that. This would be an onion and it would be negative. Cation, onion, yeah. Chemical bond. Yeah, so what I'll attempt to do on this stream. I'm giving myself like 4 to 5 hours of time for it. I'm having a double coffee for the stream after not drinking coffee for 2 days, which means it will be like drugs for me. Yeah, well, as the more extreme of people who do drugs, I just drink coffee, a lot of it, and yeah, that's kind of my type of excitement. My life is very sad, but basically, I'm giving myself 5 hours to only understand the bonds, because I do know a bit about the bonds, but I want to get this low abstract, no abstraction view into them. I know that without any abstraction, we require a lot of calculus and quantum mechanical stuff, which I'm not that interested into it, so we'll hopefully find the sweet spot. Over here, I've already found this, which is actually pretty impressive. It's actually a pretty impressive book. Fundamentals, Atomic Theory. Fundamentals which aren't that fundamental, actually. Atomic Theory is more fundamental fundamentals, it is, which is kind of funny. Physical properties of matter, acids and bases. These are all the things that you could learn in normal chemical classes in high school / college, I suppose. And then over here we have some more advanced, but still pretty chill. Oh, and over here all of a sudden fucking quantum mechanics appears, right? And that's before chemical bonding, because chemical bonding is a pain. It's a pain. The reason why it's a pain is because it's very calculusy, and no one likes that when it comes to, yeah. So all right, we have these 4 to go through, and I probably won't understand a single thing. So let's go for it. Are those all the link? No, these are just alphabetically arranged terms. Oh man. Bond theory was developed with some help from the knowledge gained during the quantum revolution in science in 1928. Felix Bloch had the idea to take the quantum theory and apply it to solids. In 1927, Walter Heitler and Fritz London, named London, funny, discovered bonds very closely spaced orbitals with not much difference in energy. In this image, orbitals are represented by the black horizontal lines. Okay, yeah. Filled with an increasing number of electrons as their amount increases. Eventually, as more orbitals are added, in space between them, the space in between them decreases to hardly anything. As a result, a band formed where the orbitals have been filled. Okay. Hi there, Elliot. Hi there. Hi, welcome to the stream. How's your day going? How you doing? How are you doing today? How are you? Hi, how you doing on this fine Saturday evening for you, morning for the rest? In the meantime, because I know there is some, what's it called on the stream, because of that you cannot answer right away because it's delay, whatever. I'll try to read this again because, as I said, I failed reading classes multiple times, so this is not an easy feat for me. In this image, orbitals are represented by the black horizontal lines and they are being filled with an increasing number of electrons as their amount increases. They are being filled with an increasing number of electrons as their amount increases. That sentence does not, that phrase doesn't really sit well with me. Eventually, as more orbitals are added, the space in between them decreases to hardly anything, and as a result, a band is formed where the orbitals have been filled. Isn't as clear. I'm an idiot. Different metals will produce different combinations of filled and half-filled bands. Okay, these are shells, subshells, I think. These are, I mean, it's easier for me to read about this than to understand these helpful graphics. I feel like I've missed on too much of the chemical law for this, you know? Maybe we should go back. The thing is, I don't want to go through this entire book because there will be a lot of things we already know. Said no, that's Nick Theory. But it would be the best example probably of that, because these are like, this is more of this redundant knowledge, honestly. Molecular mass of a molecule, isotopic mass of specific isotope. That's kind of mass of an entity, mass of a chemical formula. Okay, that's not as obvious. Average mass of a isotopic distribution. Molar mass, average mass per mole. Well, I mean, yeah. Relative molar mass actually has nothing. I really don't want to go through this entire book because it's very large and it would take me a lot of time. We didn't get law. Yeah, I didn't catch up on the law really much. You're not gonna answer how is your day going. Okay, it's fine. I'm not mad. Just understand. You know, just come here whenever you want, right? Just watch me. Oh, coffee is so amazing. I'm pretty certain it's not unhealthy, so that's good. Okay. Orbitals are represented by the black horizontal lines. The thing, this is also very confusing, because there is a difference. Shells, subshells, orbitals, right? Shells, subshells, that's obvious. That is obvious difference. Basically, each shell is divided into subshells. I can show you actually, because in my past I did that. It's still going, by the way. This one line of code is as inefficient as it gets. It's horrible, actually. Like, if I tried, I don't think I could make this code worse. So yeah, it's awful. It's really awful. But basically, each shell has subshells. Electron shells versus orbitals. I don't quite get orbitals, honestly. Shells, subshells, and orbitals. Wow, that's a video. I don't want to steal content though, like that. I'm here to steal content differently by explaining to myself mostly. As I said, I don't really understand these sort of things. After I almost graduated from kindergarten, I just kind of stopped my education there. Shells, subshells, and orbitals, because this one is not. Oh. Graphic I used to explain difference. Subshells, shell. Oh, orbitals. Oh my goodness. So orbitals are subshells. I'd rather call it subshell, honestly, than orbital. I feel like Okay then. So orbitals would be subshells. All right, now let's go back and let's, with this newfound knowledge, let's reread this. Orbitals, black horizontal lines, they are filled with increasing numbers of electrons. Okay, so these are only the orbitals. Eventually, as more orbitals are added, the space in between them decreases to hardly anything, and as a result, a band is formed where the orbitals have been filled. So if an orbital is filled, there's a band there. Very close space orbital with not much difference in energy. So band would be basically when orbitals are so close, then they kind of merge. But this asterisk is there, right? That's the you know, they merge and an asterisk, and this asterisk is basically the difference between, you know, a band and yeah. Okay. I think I kind of get it. Let me just double check though. Electron band. Double checking is always good in science. I would recommend. I don't know. That's too much reading. No, no. That's an official election path. I don't think that's quite what I'm looking for. Chemical electron band. I don't think that is the kind of band we were expecting. Band structure. That's the exact same page. Wait, do I need to divide it into orbitals too? That would be. Hi, the Tefta. I'm sorry for, you know, making a stream this early in the morning. I apologize. Fill order of atomic orbitals. So, do I need to also add orbitals there? That's so many layers of division, honestly, for this. So because here's the thing. This graphic is actually outstanding, if I may. This is an outstanding graphic. I love it. It just explains it so well. So you have, well, you do need the context for shells because there's only one shell in this graphic, but still. So we have the electron shells, which are divided into subshells. And then we have the orbitals. Okay, can we have a graphic for like electron orbitals? Because do I need to pass it again? Oh, please don't tell me I need to. I don't think I need to pass it. Okay, so this is so difficult to understand for me. This is a number of electrons. Would it appear so? It would appear so. I'm mostly targeting my streams for like relative morning for Americans and 8 a.m. confusing me. Yeah, that's what I meant. That's what I meant. I'm mostly trying to target in a way so that it would be relative morning for Americans. I would rather do it later in the day, honestly, but I just couldn't wait. I already drank a bit of coffee to get my walk done, and then I just had this high. Yeah, I want to, you know, evening Europe, morning in America. I'd love to add Asia to the mix, but I kind of am running out of time for this. It's kind of hard to get everyone in non-sleeping hours. Pacific Ocean is convenient for me in this case, but, you know, geometry jokes. Okay, these orbitals are a bit new to me. This is madness. That's what it is. It's madness. I mean, I get the idea. But everywhere I see no matter where I go, I see this everywhere. These are 3 p.m. is in the evening. I mean, yeah, but it's awkward to name. If 3 p.m. isn't, if you want to call it evening, what are you supposed to call it? Afternoon? Oh yeah, afternoon exists. I forgot. The sun is still burning me if I go outside. Listen, I'm a computer scientist. Sun is still burning me if I go outside at night. The moon reflection is killing me. All right, no good argument, Marcus. Wait, so what are these? Energy level. So we have subshells, energy levels. So this just doesn't have any shells in them. Okay, well, let's go down the rabbit hole even further. Chemical, electron, energy levels. Let's hop down the rabbit hole even more. I don't know if I'm ready for wiki. Wait a second, I recognize this. I do recognize this. This be just... Do they just represent quantum mechanics Schrödinger equation? Okay, I was misled. The cicadas are still singing. I mean, you know, if you have a cicada that can sing for you anytime, in my case. Energy levels for an electron in the atom ground state and excited states after absorbing energy. An electron may jump from the ground state to a higher energy excited state. Okay, I feel like I could really use someone that knows chemistry or quantum mechanics. Actually, this I'm learning about something in which case they both overlap, which is a bit awkward. Particles bound as confined spatially. Oh, we're getting to this part of science where they feel the need to say confined spatially. Can only take on certain discrete values of energy called energy levels. This contrasts with classical particles which can have any amount of energy. By the way, do you want some music? And if yes, then classical or electroswing or Faltrat or Stupendium. Those are the four options. It's classical, electroswing, Faltrat, or Stupendium, which are bound by an electric field of the nucleus, but can also refer to energy levels of the nuclei or vibrational or rotational energy levels in molecules. Oh boy, this is not what I'm not quite. Energy level, oh, library text, that's so nice. Yeah, I love the fact that when you are searching for stuff like these, library texts are the most often thing that happens. I mean, Wikipedia is always first, Khan is also always present, but library text the one that has the most stuff. Energy levels, also called electron shells. Energy levels are electron shells. Why wouldn't you say that? That's so much easier. That's okay. Why is it? Why am I learning about this only here? Why is it electron shell? An electron shell? I swear, why wouldn't you mention that? Electron shell is used so much. Is it a different thing over here? Electron shell. Orbit full of electrons. It is a different thing here. 2 shell, 3 shell. Don't stop giving it letters. I don't like that one bit. Just give it numbers. We all know numbers. No lot of us know letters. Quantum numbers, X-ray notation. Okay. History, electrons per shell. What is that? Composed of atomic orbitals. Okay, yeah, makes sense. Probability, density, and phase. Valence electrons, that's all I know. Well, I mean, this, actually, most of it is not that difficult to grasp. The more I read into it, the more I think that people are just confusing it on purpose, honestly. So basically, you have nuclei, which we do not care about on the stream. We act as if nuclei does not exist, because we don't care about it, honestly. What we care about are the orbitals. So you have first orbital, second, third, fourth, and whatever. That's about all the numbers I know. And basically, this is a simplified version, orbitals. If you go deeper, then you realize that each orbital, right, for example, this one right here in the middle, is made up of subshells. Each of these subshells has a different shape. There is SPDF, that's how I remember it. It's super PDFs. It's funny because PD, it doesn't matter. And this subshell is basically the shell divided into different shapes. We don't care about nucleus, exactly. Who cares? Nucleus to my work. And so basically you start with an electron cloud, then you divide it into shells, then you divide it into subshells, which are like, one of them is a circle, other one looks like this. They are funky. And all of these are divided into orbitals, which are like subshells except oriented at different angles. So all of this is just smaller pieces of the original electron cloud. All of these are just you know, part of the electron cloud. That's it. This is part of the electron cloud. This is part of the shell. This is part of the subshell. Over here we could have them oriented like different. Well, I wouldn't want to redraw the third dimension. I know how to. I'm not that good with 3D. How do I? So like this. There we go. Perfection. So if you understand valence electrons, and by valence electrons obviously we mean electrons which reside on the valence shell, which is obviously the last shell on which electrons reside in a given atom, which is a terrible definition, don't quote me on that, because it is actually very much not true. I do believe the definition is different, but it's a similar idea. Then you do know about shells, and that's just it. That's all it is. That's all there is to it. Chemists just divided the electron cloud into different parts. And orbitals are like the smallest parts of them. I'm looking for a good analogy. If it's still unclear, then tell me, because that I don't think I explained it well. Alright. Sharp principle, diffuse fundamental. Can you stop just coming up with new ways to iterate stuff? Use numbers like every normal person on the planet. Next in alphabet after F is what? Well, has such a... I swear. Okay, great. Subshells, energies, and filling order. Okay. Although it is sometimes stated that all electrons in a shell have the same energy, this is an approximation. However, the electrons in one subshell do have exactly the same level of energy with later subshells, having more energy per electron than early ones. Electrons in one subshell have... Oh, okay, I get it, okay. So yeah, okay, that makes sense. So, more energy per electron than the other ones. So, electrons in one subshell do have the exact same level of energy with later subshells, having more energy per electron than the early ones. Wait, does that make sense? Whoa, let me break down this sentence for a second. I don't... Wait, whoa. Electrons, okay, let's clean up the text first. Electrons have, in one subshell, do have exactly the same level of energy with later subshells. Well, I don't... Wait, am I the only one who's weirded out by this sentence? I mean, electrons in one subshell, right, do have the exact same level of energy. So electrons in one subshell have the exact same level of energy. So electrons have the exact same level of energy, with later subshells having more energy per electron than the other ones. Oh no, I read it wrong. Okay, I'm glad. You see, I told you, I didn't really quite graduate from the kindergarten. So basically, that's why we categorize stuff. Because in one shell we have... in a shell, we have electrons, right? For example, over here, we should have 8 of them. We have 8 lovely, beautiful electrons. And these electrons have different energy levels. No, have different energy. They have different energy. But if we divide it into shells, then we will have a couple of electrons on this shell. I don't actually remember exactly how many are on each shell. couple on these, and over here all of them have the same value, and over here all of them have the same value. That's why we divide them into subshells. So on each subshell they have the exact same value of energy. Okay, good. In one subshell do have the exact same amount of energy, with later subshells having more energy per electron than the early ones. Alright. This effect is great enough that the energy ranges associated with shells can overlap. Alright. The filling of the shells and subshells with electron proceeds from subshells of lower energy to subshells of higher energy, because they require higher energy and generally nature likes low energy. Makes sense. This follows the N plus fancy L rule, which is also commonly known as the Madelung rule. Subshells with a lower N plus L value are filled before those with higher N plus. I'm pretty certain this is just shell number, this is subshell number. Values in case of equal N plus L values, the subshells with a lower N value is filled first. Yeah, so basically, first we are filling shell 1, 2, 3, 4. Oh, that's actually very smart. Take a look at this. So basically we have, oh, that is actually very easy. Okay, so we have shell 1, right? This will be our shell 1. Then we'll have shell 2. Then we'll have shell 3. Then we'll have shell 4. And we also have subshells. We have subshell 1, subshell 2, subshell 3, perfectly drawn. And that means that this pair, 1 and 1, will be filled first. Then the next one will be this, because that's a 3. Then the next one will be a 4 over here. Next one will be a 4 over here, because this one has a higher shell number. Then it will be a 5 over here. Then a 5 over here. And only then a 6. Okay. This is almost simple. Okay. Subshell energies, I still don't think it was explained well, but okay, so that's the division of subshells. Subshells are divided. Subshells exist because we know that on each subshell, every electron in a subshell has the same energy as any other electron in that exact subshell. I feel like it's simpler than I make it. That's my name. Funny. Let's carry on. Because of this, the later shells are filled over vast sections of the periodic table. The K shell fills in the first period, hydrogen, helium, while the L shell fills in the second, lithium to neon. Let's go for a friend periodic table. I don't know by heart the link to that website. I'm pretty certain it's this, yeah, because I recognize the logo. It's a wonderful site. Lithium to neon, makes sense. Let me guess, next ones will be sodium to argon. No, it won't be. This will be a twist. M shall start filling as sodium, but does not finish filling till copper. I knew it! Next one was a twist. Sodium to copper, because next one has even more electrons. Exactly, that's the exact reason. So over here we have 2, then 8, then 1, wait, it's 2n squared, which means, wait, we first start with 1, 2, 3 squared, that's 9, 18. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I counted it wrong, haven't I? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Am I missing something? 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11, 12, 13, 14, 15, 16, 17, 18? Am I missing something? 19. Why 19? Element 9. Was it copper? Element 29. Oh, these overlap. That's why. Still doesn't make that much sense actually, because this one starts on potassium, which is over here. I won't even. No, I give up. The fertile ytterbium. The O, P, and Q shells begin filling in the known elements, but are not complete even at the heaviest known element, oganesson. Cool. Great, fantastic, wonderful, amazing. I am so glad. Two 818. I am mad because it's difficult. It's fine. It's fine. The equation for this is, by the way, 2 times n squared. In case anyone was wondering, it's this 2n squared. For 1 you have a 2, for 2 you get an 8, for 3 you get 18, for 4 you get 32, for 5 you get 50, for 6 you get 72. And that's, as you can see, 2, 8, 18, 32, 50. That's, there we go. That's something I remember. Yeah. Oh, it says it right here too. Well, there goes my intelligent insight. Okay, great. Fantastic. Wonderful. Amazing. Am I doing too much heavy stuff? By the way, you would tell me if I was doing too much heavy stuff, right? Okay, I haven't even gotten close to bonds. And we're not that far either. Entry levels, also called electron shells, are fixed distance from the... Okay, so... Occupy space, but not space between average. We usually only care about the 8 outside ones. That's where I get lost. To be fair, I have no idea why too. It's called the octet rule. Octet rule. I never understood that because it makes... No, not octet. Octet rule chemistry. It makes no goddamn sense! Do have you... okay. Yeah. I mean, yeah, that's my idea. That's what I'm doing streams. But this makes no sense, the octet rule. Although, wait, it might make sense. Wait, before we go, can I make an educated guess as if to why this rule exists? When you have shells, don't try to memorize what I'm saying right now. This is an educated guess on my side. When we have shells, they are each divided into subshells, and the first 2 subshells are S and P. And this one has 2 electrons, this one has 6, which means that if they make an octet, they fill in 2 subshells, which could be strong enough for an atom to be stable. Prefer to have 8 electrons in the valence shell. When atoms have fewer than 8 electrons, then tend to react and form more stable compound. When discussing the octet rule, we do not consider D or F electrons, only stand the S and P electrons are involved in the octet rule, making useful for main group elements not in the transition metal. Okay, an octet in these atoms corresponds to electron configuration ending with S2P6. That's exactly why. So basically, here's the idea. I don't know how to kind of put it towards. I feel like a helpful visualization would come in handy, but I have no idea how I would visualize it, honestly. Thing is, well, it's one of these things that's hard to explain, but if you get it, you get it. Okay, first of all, let me ask this question. Are subshells clear, or should I actually re-explain them, but this time correctly? Not how was it? Your weekend streams with Professor Make It. Oh, I love that. I should put in the corner like a picture of. Oh, that's a good thing to actually AI generate in the meantime while I'm waiting for the response. This one? No, this one. CD desktop project, stable diffusion web UI, Professor Make It. I like that. I like that a lot. Because this render is almost finished. So subshells make sense. Okay, that's good. That is good. So basically, just like shells can be filled with electrons, we all should remember this equation by now, 2n squared. Lovely equations, right? We get 2 and then we get an 8. Subshells can be also filled on every single shell. The config is somewhat intuitive. Yeah, because there are equations for it. It's 2n squared and 4l plus 2. These are the shells. Let me just... And this sub shells. Great. So I'm learning how to write. So these are the two equations for them. And basically, nature likes when things are filled till the end. I could do an explanation with energy states, but considering that I did like just read it on Wikipedia, that's probably a bad idea. So instead, we'll just say that nature likes when things are being filled. When things are filled to the end, because then there is no more energy. This thing it's stable. It's stable, basically. Stable energy. So basically, when an outer shell is filled, that means an element is very stable. And we actually have a name for all of these elements that have their outermost shell filled. The lovely, almost all known noble gases. Right? Because all the noble gases, if we go over here, paint version, I'll make it poster from the notes. I have had for a really long time my picture from when I was explaining. I don't think I was explaining quantum physics. I think I was explaining. Integrals. I had like this massive paint node. So basically, if we take a look, all of these are ending in. Well, argon just screwed me over massive. I was saying noble gases actually. I know noble gases are stable because of their configuration. What is their configuration? Okay, yeah. Group 18 is also so misleading because it shouldn't really be 18. Yeah, that's not really. Yeah, group 18 is so misleading because over here we should have 1, 2, 3, 4, 5, 6, 7, but we also shouldn't have that because then this table will be more, and it will be it'll keep on expanding. We should have just 1. Over here we should have 1, 2, and over here we should have like n minus. So n minus 0, n minus 1, 2, and stuff like that. Edginess video paint section was epic. That was a very simple differential equation. I cannot stress enough how simple it was. If I were to, fuck it, I'm explaining it right now. You know what, this stream doesn't make any sense and don't worry, we'll come back to chemistry. But I am explaining that equation right now because it is so simple, I just simply cannot. My channel, videos, edginess. There we go, paint. That's the... Okay, so here's the basic idea. We have E of x. Okay, this is the make it. How do you change the size? How do you change the size? Wasn't there like a size thing here? Oh, there it is. This will be a make it. Talks about something else. Place. Let me just. There we go. Let's mark it dark gray for... Well, I'm good with paint. There we go. Perfection. So basically, we have reduced the size a bit. I should fix my graphical tablet. We'll not fix it. Only plug it in. That doesn't matter. E to the x is equal to f to the x times 1.25. This could be any constant, but I just use 125. And you have f to the x, but derivative of it is equal to e to the x minus f to the x, which I'm kind of proud of this equation. It's kind of fun equation. So basically, over here, here's what we have. This segment is actually simple, right? E to the x is equal to f to the x times 1.25. This is a function multiplied by some constant. Cool, nice, wonderful. This one's a bit more tricky because we have a derivative, which is already yucky for many people, but also it is equal to this function itself, which is even more yucky. So what do we do? Well, what do we do is we basically transform it. So what we do is we bring this to the other side, right? This f to the other side, and we get f prime x plus f of x, and we replace this e of x with what it's equal to. This right here, as you can see. Let me add these as blue notes. We bring this over here, and we get, we replace this over here. And just like that, we get this is equal to, should I not do it in red? Because I feel like red might be upsetting. There we go, black. F of x is equal to f of x plus f of x, f prime of x. So remember, we are bringing this to the other side, over here, and replacing e of x with this. And just like that, we have once again an equality times 125. There we go. That's an equation, right? Now what we can do is, I'm not actually certain which direction I went. Did I divide it on both sides? I went somewhere with this. I think I divided on both sides by f of x. That would make sense. So now we have f prime of x plus f of x divided by f of x is equal to 1.25. Or maybe I divided by one. Oh, no, I did wrong direction. 125 is equal to f of x. I just divided both sides by 125. And that way, we just get dividing by 1.25 is equal to what? Well, calculator for this, handy dandy. 1 divided by 1.25 is the same way as multiplying by 0.8, which means, in other words, we can just say that it's 0.8 f prime of x plus 0.8 f of x, which is equal to f of x. And now if we just take this and put it on the other side, we'll have to switch it to minus. We get 0.8 f of prime of x is equal to 0.2 f of x. If we multiply everything correctly, we get 4 f prime of x is equal to f of x. Or in other words, well, I do believe the example with velocity is the most intuitive one. So the velocity of an object is equal to 4 times its position. So if we have a car that's driving forward, beautiful little car. This is what cars look, right? I haven't been outside for quite a bit. Then its velocity right here, this velocity. Well, I should put that as a scalar actually. Velocity would be equal to x, which is position, times 4. Wait, I fucked up. Doesn't seem right. Or maybe it is. Yeah, I think it is. That doesn't seem right though. Did I just spot a mistake in my own video? Oh, that's upsetting. I don't think anyone is nerd enough to actually correct me on this. To be fair, if someone is nerd enough to notice that mistake, then they will be nerd enough to correct me. But Oh, because I said that during the. Did I say during second, or did I say during a second after traveling 2 meters? Because that's a big difference. That's a huge difference. Please tell me that I said after 2 seconds. Because if I said after 2 seconds, then I'm not wrong. Yeah, I ended up with the same thing. It's over here. So we can treat functions basically as any normal variable or normal constant that works. Another meter. Fudge! Because obviously, if you input 2 meters into this equation, right, then, well, if you input... Actually, not that easy to... A wall from alpha. Let me... Help me. Help me double check my math, because I don't trust myself. If I already... I'm pretty certain after 2 meters it won't have... Alright. F of x is equal to 4f prime of x. This seems like a basic thing, it should be here. F of x is equal to 4, then the equation for it is solution. Well, so there, oh yeah, there's isn't really a normal solution for it, is it? No. F of x is equal to constant e to the x fourth. Yeah, that seems right. Desmos.com. We will ignore the constant e to the x fourth, and after 2 meters, right? It's not. This isn't. Yeah, I messed it up completely. This is completely messed up. Yeah, oh my goodness. You idiot. The differential equation conclusion was a total mess. Do not ever even attempt to try this sort of thing again, because you look right now like a complete fool. Disliked, unsubbed, will never watch a live stream again. Merry Christmas. Alright, there we go. Pin. I haven't pinned the comment yet. Okay, cool. Great. Great, alright. Now that I achieved the status of an ultimate nerd because I commented my own, I could have just solved. Oh, it's obviously e to the. It's obviously e to the. It's so obvious because e to the x derivative of e to the x, right? If you have this is equal to f of x, then obviously f of x is equal to e to the x. Everyone knows that. Everyone knows that. So if it's 4, right? Yes, I just cannot even. I just cannot even. I could have gone with the comment 2 ways. I could either do passive aggressive or aggressive. So I chose aggressive. It should have why did I stop there? It was such an easy solve. That was the simplest differential equation in existence. I should do more differential equations because it's getting ridiculous. But I do believe that then people will not tune into my streams at all. Chemistry is kind of cool, you know. Some people do enjoy chemistry. But differential equations, that's where you lose. That's where you lose subscribers. Alright. Wasn't this actually? Oh. I love how close these are. to just a linear plot, but no, chemistry wouldn't be that simple now, would it? Cool, cool. Ah, great, fantastic. Alrighty then. You were being edgy. No, but I do feel bad. It is you have to believe that when in the world of differential equations, it's like the basic thing in existence. I mean, for goodness sake, Elliot was joking about that for so long. About the fact that e to the x is derivative of e to x is equal to e to the x. That's like one of the first things you learn when it comes to differential equations. I am so mad at myself right now. Nah. Alright, chemistry. Back to chemistry. I swear. So that's the octet rule. Basically, when octet rule is nice because 2 subshells are filled already. So, you know, then these atoms are stable because 2 subshells are completely full, and nature likes when things are full like that way. So after octet rule, I suppose the next one would be the give me a second. The octedecillion rule. That would be the next one after the octet rule. So basically things like when there are only 2 things, that's what sum of the atoms. They like when there's 8 of them, and the next one would be the octedecillion rule, because that's 18, and when there are 18 electrons, then 3 of the subshells are completely full, and that's what atoms really like nicely. For most atoms, there will be a maximum of 8 electrons in the valence shell. For most, that is such a that I don't like that. For most atoms, there will be a maximum of 8 electrons in their valence shell. Not really. I mean, I'm pretty certain, from what we've read, it's basically from potassium up, there can be more than 8 electrons in their valence shell. So, I don't like that one bit. The fact that they mentioned that this way. For most atoms means these, because that's what you learn mostly at school. At school, they really often mislead you with these sort of things, because they don't think you should know the whole story, and because of that, they just tell you the simplified bit, which makes it really hard to get into it later on. Okay, cool. We've got this far. Let's carry on. Chemical bonding. Fundamentals. So we have the bond structure. So apply it to solids. Bonds, very closely spaced orbitals with not much difference in energy. Orbitals are represented by horizontal lines. Okay. Different metals produce decimal combinations of filled and half-filled bonds. I feel like you're just trying to confuse me at this point. Sodium bonds are shown with the rectangles. Filled bonds are colored in blue. As you can see, bonds may overlap each other. The bonds are shown askew to be able to tell the difference between different bonds. Convenient. The lowest unoccupied bond is called conduction bond, which would be this one, I assume. And the highest occupied band is called the valence band, which I assume will be this one if you mean fully occupied. If you mean partially occupied, then this one. The band will follow a trend as you go across a period. In Na Phrygianism is half full, full, half full. Okay. So it will be half full, full, half full, full, half full. Alright. I can respect that. The probability of finding an electron in band is shown by the equation. Cool. Delta E in the equation stands for the change in energy on the energy. Okay, it's actually not that bad. As the bonding constant. Okay, it's not that bad. Could be worse. Okay, then it could be worse. I like it. So if this is equal to 0, that means you'll definitely find an electron. which I assume never happens, but okay, it's not that bad. It's not that bad. Okay, let me turn off the screen for a second. And actually, no, we will be taking notes in space, life, and time. What is the bonds are? I don't like it. That's neat. Okay, let's read one more thing about bonds, and then we can do this basically, which would be bonds. Bonds, if I may. Bonds. Thank you. So let's read some more about bonds to make sure that I do understand this and not just pretend to understand for fun. I don't know. Electron bonds. My brain really hurts, which is fun. It's not my head, it's my brain. It's festive. Oh boy. Well, ain't you a treat? Is that Hamiltonian fully described the system requires the inclusion of the interaction between electron ions and is given by. Wait, that's actually amazing. And there's a simplified Hamiltonian. Wait, this could be so useful. Oh, this could be so useful. Because if this is what I think it is, it could mean that I won't have to actually write any complex data system for my generator. I could just plug in the equation. Well, not plug in, it's obviously more complex now because calculus and programming really hates calculus, but in solid, it's only in a, I dislike that, but it's fine. In solid, the free electron approximation is no longer valid. Why is that lock next to it? Restricted permissions. Youch. Semiconductors. Schrödinger fully describes the behavior of electrons when appropriate Hamiltonian is used. Yeah. Hamiltonian that fully describes the system requires the inclusion of the interaction between electrons and ions is given by. A lot of fun here, as we can see. Where the ME is the electron. Okay, but wait. This is for what part of the behavior of the electrons? Because certainly won't be all. Ion separation between ion and electron strictly solving this Hamiltonian is very complex. Yep, that I can see why that would be the case. I feel like yeah, I can understand why it would be complex a bit. Are usually employed to simplify the task. Important approximation, Born-Oppenheimer approximation, the one electron approximation, and the mean field approximation. The Born-Oppenheimer states that the electrons react instantly to the motion of the ions, but the reaction of the ions is much slower, allowing us to ignore the motion of the ions. The one electron approximation assumes all electron interaction have averaged, and the mean field approximation states that all electrons are in identical surroundings with regard to the ions and their equilibrium positions. These approximations allow us to use simplified Hamiltonian. Okay. But it certainly is simplified. I think we can all agree on that. But what I'm looking for is, oh no, it's that bad, isn't it? Is it this symbol? Please tell me you'll tell me the LaTeX if I... No, you won't? Oh, you will. That's neat. We're looking for H-bar. H-bar, nabla. That's what it is. This symbol is horrible whenever you see it, because the differential operator given in Cartesian coordinates xyz on a three-dimensional Euclidean space. It's pain. It is pain. Because, you see, yes, IJK, yeah. I JK not when it comes to this, because it's not fun. It's a bit, whenever you see it in math, that means you should just run, because that's it, just run, just if you run. Yeah, boy. Oh boy. I will not even, listen, I'm not even pretending I understand this math. Let's be real. I mean, I understand bits, but only bits. The thing what I'm looking for right now is if it will be useful to read this first. Energy levels of the market can be described by called band. Energy bands can be classified as empty, filled, mixed, or forbidden. Energetic. I feel like all of these are self-explanatory, and the energy levels are occupied by the electrons, distributed according to Pauli exclusion principle. Starting with the lowest energy value level, electrons that contribute to the electrical conduction occupy the higher energy bands. The valence band corresponds to the highest energy band that contains electrons. No, this is not filled. Okay, good to know. Valence band can be fully or partially occupied. Actually, partially. The allowed empty, say, I have to take the small win, okay? This entire page is way more advanced than I am. Way more advanced than I am in general. So, these small wins count. The allowed empty states in the valence band add contribution to electrical, and the conduction band is the lowest energetic band with unoccupied states. I feel like if I were to read this entire, not page, on the website, it's I swear, why would you look at it? Why would you restrict the why would you block knowledge? Don't block knowledge, I need it. Fun, actually it's pretty fun because I still have no idea what will help me. I'm looking for a kind of generalized, simplified way to describe electron behavior. Density of states represent a high number for the energetic states. Trying to be if there are no available states for occupation, the general level value and density is zero. Cool. I love that because it looks like it's drawn in paint, but I'm pretty certain it's generated. Just kind of funny. Didn't microscope, or maybe it's even measured. Oh damn, that would be impressive. Holes are fictitious particles considered positively charged. I still have no idea if this is what I'm looking for, actually. This is because this is all about conductivity. Conductivity in depth may add, but I do believe that is pretty obvious at this point. The concentration of charge carriers might be increased. The process is possible by introducing impurities in the silicon crystal. It's called doping and gives rise to additional number of electrons or holes in the semiconductor. The doped semiconductor is called extrinsic. After reading this entire thing, I have no idea. I mean, if I had access to this, that would be so great, but I don't, because it's very fucking hard to give it a username. Sign in to view this page, I swear. Let me guess, this you just get, yeah, it's from, so upsetting. It's so upsetting, because this seems like such a great thing to read. Boy, boy, oh boy, oh boy, oh boy. Should I go just look for quantum mechanics on lab text? Not chemistry, just physics. Quantum mechanics, and I would. Should I just. Because. These are just chapters about quantum mechanics, which are not quite. These the same. Wait, these are the same picture as this book. Wait, that's not the right book. What did I just read? This one. Is it the same picture? Huh. Okay. Quantum mechanics. There's just love. Okay, quantum mechanics 3. I haven't even read the second one. I feel like I would be very confused because I wouldn't know the plot exactly. Alright, introduction. Okay, let's go for it. Fun. What is probability? What's the scientific definition of okay, let's do this and let's go back to basics, back to basics. Probability, okay, base abstraction. No, we do not care about that. What we care about is only going for the abstraction -2. Exactly this. And over here we'll be just adding things. What is the scientific definition of probability? Consider an observation of a general system S that can result in any one of the number of possible the outcome the set similar matter current sigma S x ratio exhibit limit infinity symbolically. I think we all understood that pretty well. We all know that probability there is just this is just, you know, this is just generalized way. Well, not generalized, but actually specialized, I would say. It's more of a defined way. See, I know a lot of smart words. Omega, sigma, no number of systems and some, yeah, cool. Yeah, great. Do I really not have the arrow rendered on my screen? Oh, that will be so annoying. Two distinct possible outcomes, x and y, observation made of system S, probabilities of occurrence px, py, respectively, as determine the probability of obtaining either outcome px or outcome py, which we shall denote px, py. X, y is number of systems. Okay, yep. Does this, great. Which means that the probability of obtaining either outcome S or the outcome Y is the sum of the general probabilities of X and Y. For instance, the 6-sided dice, the probability of throwing any particular 1 to 6 is 1/6. Because, yeah. 1 or 2 is simply 1/3. Great. These are basics like that. Normalization probabilities. That is actually an interesting way to put it. I haven't really. It's with a sum. I usually see it with an integral because I do believe with an integral is more intuitive for this sort of thing. But what it basically means is that this entire thing basically says something must happen. So if you throw a dice, it is impossible to get all the probabilities to add up to, like, I don't know, 6 sevens, right? So if we have a 6-sided dice where each side has 1/7 probability of, you know, when the dice has a probability of 1/7 of landing on each side, then we have 1/7 plus 1/7, because we can get a 1, we can get a 2, we can get 1/7, which means we can get a 3, like this, 1/7 because we can get a 4, plus 1/7, 5. It takes me way longer to draw this than is actually required. I feel like the point is pretty self-explanatory, but oh well, I restarted. 6, then what we get is we get 6/7 as the probability of everything, which is impossible because that means that there is 1 in 7th probability of nothing happening, which, as we know, is rather silly considering that the dice must fall on some side. And that's why, basically, that's what it says, that if you add together probability of every single event, it must add up to 1 because something must happen. Normally it's with an integral because usually in quantum physics it's about, integrals more than sums. Well, that's not true. It's about functions. Oh, there we go. It's about functions. Functions are better defined with integrals than sums. And not defined. I don't listen to what I say. Just trust me. That's determine the probability of obtaining the outcome x in the first system and obtaining outcome y in the second system, which we shall denote x. No idea why. I'm not that much of a nerd. I don't know the names of every single operator in math, although it would be fun. In order to determine this probability, we have to form an ensemble of all the possible pairs of systems that we could choose from the ensemble sigma. Let us know the ensemble sigma. Yeah, sigma. Number of pairs of systems in this ensemble is just the square of the number of systems in the original ensemble. So, oh boy, this is very heavy in comparison to how basic it is. Furthermore, but I like that means the entire book will probably be really good. Furthermore, the number of pairs of system in the ensemble sigma dot x sigma, I'm certain that's the name of that. Don't double check me. I'm always right. In that exhibit outcome x in the first system and the outcome y in the second system is simply the product of the number x is the number of system outcome y. It's an neutral example so that x. Yeah, cool. It follows from the basic definition of probability that this is basically a very, very, very correct way to say that this is equal to this. Like a very, very, very correct way to do it. Like very mathematically correct. For instance, probability of throwing 1 and then a 2 on a 6-sided die is 1, 6, which is equal. Yeah, so basically throwing 1 twice in a row, or throwing, I don't know, a 5 twice in a row, whatever. That's what it says. So for those two independent things to happen, that's just multiplying probability, which are very basic things, but they are explained so thoroughly in this. This is fun. What is meant by the mean or average of a quantity? Suppose that we wish to calculate the average age of undergraduates at the University of Texas at Austin. Shout out. We could go the central administration building and find out how many 18-year-olds, 19-year-olds, etc. were currently enrolled. We would then write something like, yeah, makes sense. Where 18 is the number of enrolled 18-year-olds, etc. The probability that random pick student is 18 is, now over here, this is just the averages. Where n students is equal to number of students with different ages, big surprise there, number of n of students, just number of students, is the total number of students. Actually, this definition is only accurate in the limit that n students is very large. That will be averages, that's how they work. We can now see the average age takes from, I mean, you do have to realize that I am, trying to add this comedic spin to it because I'm making an entertaining stream, but this is actually really extremely well written, and I do want to say how much I respect that. This is amazing. Finally, because there is nothing unique about the age distribution of students at UT Austin, for a general variable u, which can take on any one of m possible values, corresponding probabilities, the mean average value u, which is denoted expected, if I'm not mistaken. That's the expected value. I am really not used to seeing that without an integral. I really often prefer. Yeah, it is really good. It's very correct. That is kind of it's extremely correct. Most of these things could be explained really simply, but it's it wants to make sure that you know what it's talking about. And also, yeah, but the one thing that actually is not really sitting well with me is the fact that it's using they are using sigmas everywhere as sums. Meeting soon. All right, Tefta, good luck to you. I'll be here and doing more fun stuff, which I'm actually going further away from my goal for today's stream with every single second that I delve into more quantum physics, which is probably a mistake. I should probably leave quantum physics for a separate live stream. This is a good book though. My only thing which does not sit quite right with me is the fact that there are sums everywhere, which I don't stay sane. I will not. So I'll try my best. It doesn't stay quite right because everywhere, as you can see, there are no sums, there are integrals everywhere because it's functions. And calculate expected values over here. This is the same thing. Expected value. It's this right here, except we are using an integral for it because that's quantum physics. Actually, that's not only quantum physics. That's just anything working with a function. Just like f null is equal to x makes no sense because function is input provided the operators can be used without function. That's actually entering in your YouTube channel. Mr. Beast Twitter context. Wait, what is that? I don't mind. I want you to know that, but I'm just curious. Mr. Beast Twitter contest. What's this? Mr. Beast on Twitter. Can I don't really use Twitter, so I'm very sorry. I would if I were, I would know about these things, but I'm not hip with the youth. I am just an old man trying to make an honest living. What is Mr. Beast Twitter contest? Oh, there's money info. No, that's the wrong thing. That's obviously I was kidding. Do you have a link? Has a subscription I pay for, and if you subscribe, he makes contest. Oh, do you have like a? Okay, can you give me like a short explanation? Because I know you're busy. I really don't want to take up your time when you're going to a meeting. YouTube channels. Tefta, did I mention like how much of a fan I am? Did I mention how much I love you, Tefta? Did I mention that today? Everyone, I would like to, just that's Tefta. I feel bad, honestly. I don't think I'm doing enough stuff. I have to work harder, honestly. What am I doing? Right? I'm doing quantum physics. I shouldn't do quantum physics. I should finish the molecular generator, for goodness sake. No more quantum physics. We are doing only bonds. We're doing only bonds to finish the molecular generator to have something done. Right. We have to end that everything that Tefta does for channel. I have to end it. Have to do some work. So bonding. Atomic bonds the creation of atomic. Oh, let me see. That's the only kind of response I can give to that picture. I am speechless. Thank you. I don't know what to say. But that's the only response I can give to that. For you're watching at home, you will know what the response is. You will not know. Creation of atomic bonds in depth, but like extreme depth. Maybe Khan Academy, maybe Britannica, yeah. I love that when you start researching like these, more strict kind of area of study. The heavy ones, then you start getting source. Then the only sources you start getting is just Khan Academy, Britannica, LibraText, and Wikipedia. Those are the only four. Or some government like projects and stuff like that. Or from time to time university things, but most of them are locked, which is upsetting. First complete attempt to describe all matter in terms of atoms and their properties. First complete. Well, I'm sorry, I ain't got the money. I have to save up, so I'll donate $200 to charity. I am saving up for that. First part is just that all matter is made of atoms, which these are very basic ones. This is very basic. No, it's not really that in depth. Entropic bond. Oh, there are more bonds. I want a generalized, a semi-generalized at least. Particles predict a great diversity of complex crystal structures via self-assembly. Obviously, there is more. I need more coffee. My frontal lobe started itching like 10 minutes ago, which I am not quite comfortable with. Alright. Yeah, because it's... I'm sorry, neighbors. Alright. Yeah, my frontal lobe hurts. I know I like that. But it's fine. Listen, if you can't feel different parts of your brain, that means you are doing something wrong. No, not neighbors actually. No, what did I say? No, I know it was kind of neighbors. Don't get that. Doesn't matter. Point being, I prefer quantum mechanics because of that. Everything's like it's simple. You don't have these like every chemical bond. Can I like get every chemical bond here? Is there Wikipedia? Oh, Wikipedia will have a list. We have ionic covalent, so electrocovalent, covalent, metallic, intermolecular. There's chemical bonding. In the unrealistic limit of pure. Okay. Cool. Yeah, if I'll go with these bonds, then I'll have to create some sort of data system for this, which I wouldn't really enjoy that much. Bond length energy, cool. Intramolecular forces that hold atoms together in molecules. Strong chemical bond is formed from the transfer of sharing of electrons between atomic centers, and relies on electrostatic attraction between the protons in nuclei and electrons in orbitals. The types of strong bond differ due to difference in electronegativity of the constituent elements. Electronegativity is the tendency for an atom of a given chemical element to attract share electrons when forming a chemical bond. Where the higher the associated electronegativity, then more it attracts electrons. Electronegativity serves as a simple way to quantitatively estimate the bond energy. Wait, that's actually very convenient. Characterizes a bond along with the continuous scale from covalent to ionic bonding. A large difference in electronegativity leads to more polar ionic character in a bond. Roll up and put on your controller. It's Chairman of the Board by Stipendium. How's this doing? No, it didn't finish yet. 94 out of 118. Okay, cool. It's also abstract. That means it was obvious that was abstract, actually, to be fair. A covenant between two is stronger than the average of A and B bonds. According to the valence bond theory, of which Pauling was a notable proponent, this additional stabilization of the heteronuclear bond is due to the contribution of ionic canonical forms to the bonding. Yeah. Cool. Cool, very cool. I enjoyed that. I enjoyed that sentence. I did like it very much. Actually, outstanding. I'm doing for an hour and a half. I got nowhere. I've learned a lot, but still I got nowhere. There's underlying quite accurate semi-empirical formula for decision energies, namely this thing. A more accurate fifth. 1/3. You know that something is good when they just throw in a random constant. Okay. Alright. I actually do believe that they threw in 1/3 over there, because if you get square root of 2, you get 1/4, 1, right? And basically, if you were to yeah, because that's a switch. They multiply root and multiply times 2, multiply both together, then times 2 rooted, and they have to multiply. Actually, no, that's dumb what I just said. That's very idiotic. I'm sorry for that. There we go, electronegativity. Fun, festive. These two elements have the same electronegativity, which I do believe should serve as a prime example of why this is very much a simplified thing. Because when two things, which are one period away from each other, have the same electronegativity, then something is up. Should be, okay, great. I don't know. Where are we? This 95. How long have we been 95? I do believe that we might be stuck. Electrostatic potential map of a water molecule where the oxygen atom has more negative charge, red, than the positive blue hydrogen atoms. I don't want to learn more chemistry. I don't like it. There are certain things that we all want to know but not learn. So, this is one of them for me. Great. So this is no help. Alright, let's just do for covalent bonds and ionic. Covalent bonds and ionic bonds. It won't be great, but it will be almost alright, so I'm all for it. But let's not use Britannica, let's use something different. Also not Can. Libotex, I like that. Oh, there's just one about the ionic incovalent, but this will be generalized, right? This is general overview, not what I'm looking for. Once validation to clinics, net charge of the resonant compound is 0. Oh yeah, we can also calculate the charge and stuff like that. Cool. Yeah, this is what's so weird about these things. Over here, magnesium. It has no electrons, but yet it's still a bond, because why not at this point? The real big issue with this system, alright, the real big problem is that I'll have to create some sort of data system, which is upsetting. What do I mean by data system? Well, let's go for it. Well, basic gen this, and we are still stuck on 95th, which is terrifying. Because we still have 23 more elements to go through. Fudge. Normally I would debug this and I would add like a percentage sign of how many percent we did, but this time won't be able to. I can't, because it's all in one goddamn line. All right, let's stop it. Let's optimize it, because I just cannot. This one line was fun, but not now. It's not fun. It's not fun anymore. Let me just comment how does. Yeah, there we go. That'll fix it. Fix it. So basically, what we need. Let's this time do it normally without something like this, maybe, because I feel like it's just, fuck me. All right. So great. We have noble things, right? Noble. There we go. This is basically the way it will look like. No, just right. So yeah, I need a Python break. I simply cannot anymore. DuckDuckGo, and I would like to get Python dissect string. There we go. This is what I am looking for. These are words, not quite. I am looking for, actually not dissect, wrong word. I'm trying to take out the middle of it. Extract a string from a string. Nah, dissect, good enough. Actually, wait, I can do it. Oh, I can't actually do it, because I can just. Oh, this is such a mess. Love it. So, first of all, we will take element cell. Which one? We will take number. First, let's do it manually. Well, let's do everything manually, because that will be more convenient. Which be noble char and noble char corresponding to them. And over here we will just take step by step. Am I looking for something? No, I'm not. Good. Pass backup is also here, in case I ever wanted to use this. It's cleaner. I suppose final string array is not the worst thing that happened, but oh well. We'll use this. And first of all, helium, which has this electron structure. I should have actually remembered that. So this is the first one. There we go. Then we have neon, which has this, not this. Neon, which has this electron structure, which will be exact same as previous one, 1s2, and then this. Lovely. Then we have argon over here, F metal, argon, this, which will be exact the same as neon, except it also has these ones. Big surprise there. You won't believe what the next one is. It certainly will not be the same as this plus something. Krypton, night. Over here. You're up against the chairman of the board. There we go. Xenon, which will be the same as this. And we're almost there. With Ruben, if I'm not mistaken, I think. I may be wrong. Let's check. Radin, I'm such yeah, that's what happens. Boom. Great. Now what we can do is we can actually do it a bit simpler, because we can just basically replace the strings with what we see. So if I add open brackets over everywhere, like everywhere, great. Then if I, oh, this line is such a mess. Let me just copy, paste, and let's call it rename fast, because it'll be fast. And let's delete this line because I cannot. Oh, so much cleaner, isn't it? There we go. Beautiful. EC something, there we go. That's what we are trying to figure out. Well, not trying to figure out, we already made it once. So now what we have to do is we have to take element cell 5, if I'm not mistaken. 0, 1, 2, 3, 4, 5. Would you look at that? It is 5. Cell 5. This will be a string. Element string. String is equal to this. And for I in range. No, wait, for noble in noble cha. No, for I. I'm sorry, I'm very indecisive. Range, length, this close twice, and just have fun. Noble cha and I into it. And over here, let's put a conditional. I have a very low definition of fun, don't I? Oh well. For if our element string dot split, I think that's what it's called, right? I think it's split. Sentence split by, yeah, okay. So split close bracket 0 is equal to this. Then tell me print for now. Print f string, these two, element string 1, no wait, messed up, element string 1 and noble cha corresponding I. Oh yeah, that's true, this one should probably be these. There we go. Oh wait, pass fast. We got nothing. That's festive. I like. Yeah, great, fantastic. It's wonderful, amazing. I think, but we got nothing. So let's also print these. I feel like this could help. Print these. Well, f string print obviously. And I actually don't know why I did an f string. I could have just now. It doesn't matter. Oh well. Print. We get a lot of spaces and a lot of weird characters. I don't know if I like that. I do not know if I like that, because that does not seem quite correct, does it now? It should return an array. What happens if I just return 0? Oh, because it's the fourth one. I'm such an idiot. Ah. How about now? There we go. That's, yeah, great. Now we're great, because we have basically let's just call it full string is equal to something, and let's just set it equal to this. festive. Oops. Now that we have the full string, very sorry for that, we should just dissect it again. So, this is actually so much simpler. I will still will be a bit meh. Oh well. We'll have 3 arrays. Shells, subshells, electron numbers. And this actually won't be an array, this will be... Oh, no, wait, this will be an array. There we go. Shells, subshells, electron numbers, and now basically we take the full string and for a mini string in split space, but at the same time we do want to... Oh, wait. If full string is not equal to predicted, or because calculated, or full string is not equal, and almost made a big mistake there. Full string is not equal to, if it's not equal to, not full string, that would be rather silly. Calculated, there we go. If it's not equal to both of them, then what we do is we do this. Shells append full string 0 as an int. Because this would always be a simple int. Then what we do is we do subshells dot append, and we append what? Well, we append the first one, like so, except we can't because this will just give us a letter. We don't want a letter, we want a number. And this one should be also -1, by the way, because that will be important later. We want a number. So append 0 if full string 1 is equal to an s, but the string s, else, and we just copy this over here, s p 1 else d2 else 3f, actually no, over here it should be just a 3, append and let's append 0 if full string 1 is equal to s, then append 1 if full string 1 is, and just remove these, this should be simpler. There we go. This full string now the issue was literally only with brackets, cool. And then shells, not shells, only electron ln append int full string 2, so this, if length of full string is not equal to 4, else append int of this. Which would look like so. And just like that, in the end, let me just... Well, in the end, I should just iterate through every single one and then find the highest. All right. For a shell in shells, if so, highest shell, highest sub shell. That's all we care about. If both of them should be a 0. If highest shell is smaller than the shell, then we just highest shell equal to shell. And you won't guess it. You wouldn't be able to guess it if you tried, but we do the same thing for subshells. Damn it, I missed sus. Not what I meant. Subshells. Subshells. Wrong. Damn it. What's wrong with me? There we go. Highest subshell. Then subshell is equal to shell. There we go. And just like that, we have the everything we need. Yeah, this entire massive line of code, by the way. That's all this. That is it. That's it. This right here. And I just coded that in what, 15 minutes? That's it. And now for the last bit, which basically means create the entire thing, which would mean, how did I do that actually? Oh yeah, I did it with an with an inline string. That actually could be convenient. With an, how and what now? Well, how would I do it? How would I do it? How would I do it? Well, I would go through each and every single one of this in this array, and then I would add it to the appropriate place. Yeah. Okay. So over here, let's add the for I in shells, in range length shells, right? Let's add what? Well, let's add another array, which would be for I in range length sub. Actually, no, it doesn't matter. It don't make much sense. So right now we are iterating through every single one of these, and we are doing what with this? Well, oh wait, no, that's right. Highest shell in range highest shell. There we go. Now we basically created enough arrays for this, which is great. And in this array, that's more difficult than I thought. Nah, why am I doing it on a single line like an idiot? Array of arrays. What does mean? It starts with capital letter. There we go. Array of arrays is equal to, you won't guess it, but an array. And in this array, we will do for I in range, what now? Well, highest shell, obviously. And then we basically do array of arrays dot append, and what we append another empty array because we are fun like that. And then in that empty array we do what exactly? Well, we iterate through the entire thing and we look for I in range highest sub shell, but this should be a subshell for the appropriate. That is true. That is actually true. That is true. Fudge. Should be the appropriate. Why is it so? Why is chemistry so complex? It's almost as if the entire existence is a bit complex. But that couldn't be. That couldn't be. That's impossible. How that ever happened? I'm sorry for that. That was very. Let's see. All right. has subshells, it has to be an array. Yeah, it has to be an array for each shell, which means for highest in shells? No. How did I did it the first time it worked? That's actually impressive. I have no idea how that, I did it on a single line. I cannot do it right now. To be fair, my brain bends right now, which is absolutely, it's not my, I don't feel it in my head, which is weird. Normally you feel like your head is about to explode. No, I feel bending in my brain. On the inside of the skull, which is quite graphic, will not lie. But how did I do it? How am I supposed to do it? How are things even done? Do we have free will? Well, in order to get answered that question, I would really recommend you check out my video. Do you have free will? Always be sure to promote that. I know I've been quiet, but my brain just froze. I cannot think. I've reached my limit on thinking today, which is not good. I haven't finished it yet. I did finish this on a single line quite well last time. And if I only had that single, we might have that single line. Because if we take this, right, if we go for, no, backup, you're right. If we go for Control F, if you go to pass, if we replace this entire thing with, what's this called? Oh yeah, copy, paste, let's just call it walk thing might as well. And if we now, it appears a couple of times, but basically if we de-obfuscate, I do believe them as de-obfuscate, right? I don't know. I'm not hip with the youth. I don't know what kids call things these days. Walk thing, yeah, exactly over here. Now if we just put it like this, and we get a couple of errors. That's why. No, we don't. Final string array. There we go. Now, no longer erroring, by the way, because it's finally large enough for my code to understand it. Now we have this. There we go. We're getting somewhere. And now we have this thing, which is the last one. There we go. If element is not called else1, we do not care about these. And so this would be the one line thing which does it for us, but this is also has some additional things which we do not need. So what is this line exactly? In the list filter lambda, so we are filtering out the nonce which are oh, this is actually well written. This part, the rest is garbage, but this part is actually quite well written. Highest shell index 2 in range, final string array. So we could just give it final string arrays and figure it out. So let me add this to it. And let's over here set it equal to this. Except we don't have final string arrays. Final string arrays being... Actually, I'm presetting these. This is what they are. Final string array 3 pass walk thing. There we go. Wait, no. If element cell 1 symbol is not equal to hydrogen and helium, then this, and then print Alright, so we get step by step. 1, 1, 2, 1, 2. These are shells, so final string array are just shells, except everything added 1. So shells with everything added 1. These are the subshells. And these are just the number of electrons, but as strings. That's interesting. Because I did, that's why it is here. Okay, cool. So, shells but without the -1. That's what we need. Shells do not need the -1. There we go. And now 3 are the electron numbers. First are shells, but let's just first get all the 3s we've got. That's it. These are shells. German of the boards. There we go. This. Cool. And subshells. Please walk. To be fair, that is actually quite obvious hiccup. Base 10s, we got an S. Not great. Print no, I don't know. Shells subshells and electron numbers. Wait, what is it breaking? Append in full string 0. That's where it's breaking. S? How is it possible? How is that possible? Split by spaces. Print mini string. Something that is not, no, that is, no, don't do that. Full string is supposed to be this, not something. Oh, I know why, I know why, okay, I know. So let's give it instead, let's instead give it 1s2. Would you look at that? Well, that's not, I know what this error is actually, I know what the problem is here. Is the fact that it's a reference, we have already had this issue. Now every single thing in the table will be the exact same element, with nulls everywhere and everything. Yep, and that's due to the reference thing, which deep copy atom template. Nothing is being changed basically. May I ask why? It is made with deep copy. I have no idea. Let's comment this out. How about now? Table. Everything is still a no. Why? Why? It's not supposed to happen. I'm making a deep copy on the beginning of an atom template. Do nothing function. I do believe I should get rid of that. I is equal to 0. Why is I is equal to 0 here even? What's the point? Predicted is also there, which is just festive. That's why it's there. Yeah, I'm getting the issues. Let's instead do it this way. Let's give it a 0 first, and then let's set it equal this. Set it equal to integer value of this. How about that? It seems. In full string. Oh, it's full string. It's supposed to be mini string. Oh, I'm such an idiot. Oh, I'm such an idiot. Oh no. Oh no. Oh no. 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 There we go. Now it broke. Cool. Fun. Index out of range. Mini string 0. There is no mini string 0. There's just a string with nothing. That does happen. Yeah, it does happen. So let's just do it. Let's just fix in the worst way possible. And length of mini string is not equal to 0. That's the best. Yeah, best way to fix it. There we go. Everything works. Great. That table, if I may, it's still empty. It's still very much empty. No idea why. The table 1. Let's call it the table 1. And the table 1 is empty. It's empty. There's nothing there. Why is there nothing there? There is an organism sometimes in the completely wrong place. There's an organism, but apart from that, everything is empty. so close to going absolutely mad. Alright. Atom template, deep copy, atom template, that's what atoms are. Yeah, it should be correct. It's not though. It says this does not have to be a float. This can just be there. There we go. These are all correct right now, actually. Well, kinda, but these are 0 when they... No, wait, they should be 0. But these are... Yeah, because if we do the walk thing, then we get... Oh no, they're actually very much correct. I mean, there's another issue then, somewhere in here. Oh, so close to flipping completely. Over here we have, it's correct, this we have correctly. That's just, I don't... Have this to look at for now. Private chatting. And here, let me just... Oh. Could you please tell me why this code produces corrupted output? And just give ChatGPT the code. Actually, no, fine. There you go. Variable overwritten within loops. So the variable I used for both the out loop and the inner loop. Inner loop variable something. So I'm using. Okay, I should have spotted an error like that. To be fair, that does seem like something rather simple. I am using it twice. That is true. Capital I. That's such an idiotic error, though, to be fair. Oh yeah, because we have to replace it everywhere over here now. Yeah. AN is equal to this, because oh, that's why I is equal to 0 was there. Makes sense. There we go. We have everything. Would you look at that? Except these, because we don't have them yet. Because I was terrified to uncomment this, but let's uncomment this. Let's get it rolling and it breaks. Cool. List index out of range. Festive. It didn't break for the first couple until we got here into the land of the trees, the freeze land, if you may, and I will may, and I may. List index out of range. Which one? Which list index out of range? Because I'm not that hot about like going through all of this, honestly. Okay, what is new about this? Well, we get a 001. We get 1 in the subshells. That's what is new. Highest shell. Wait, highest shell index. Wait, is this entire thing getting a highest shell? It is. I can just change that to be 8 shell, and that way this code will be much cleaner. H shell, which is not a thing yet, but now it's a thing. There we go. H shell. Yep. If element. Let me go that. Yeah, that makes sense. And this is just an error. Okay, I have still no idea which one's which. Can you like me which loop breaks? Because that would help. Fine, I'll have to unmess this mess. Let's unmess the mess. Oh boy, my brain is on fire. Not the good kind. Not the good kind. Alright, let's do it step by step. If this, then, and else, boom, and boom, and boom, boom. There we go. Cool. Now what will it be equal to? Well, this line obviously, but we should reduce it a bit so that for I in range maximum, I feel like this H shell might have used that incorrectly. I did. Cool. I did use it completely. Well, wait, maybe I didn't. For I in range, oh no, this is, yeah, okay. For I in range, maximum, yeah, because this script is like looking for a highest shell. I had no idea. That is, who wrote that? That's so horrible. For I in range maximum out of an array of integers, highest shell index 2. What's highest shell index? This is looking for the highest subshell. Why is it outside? Why is this inside? There's so many questions. This makes no sense. This entire code makes no sense. Absolutely none. Why am I first doing subshells and then shells? This is so garbage. This is rubbish. Complete rubbish. That's what it is. Horrible. Who wrote that? It errors too, which is great. Right, if we were to do the walk thing and then stop it like right away, what's the difference here? The difference is 112.011.221. 122. That's actually an error. Ooh. Shells. 122 on the first one that has 3 by 3. Huh. First one that has 3 by 3, which would mean not lithium, only boron. 122, that is correct. 112, what is 112 referring to? Subshells. That's the issue. I messed up subshells and shells. Okay, so that's why it didn't seem right. Okay, so these ones should be shells. Shells. So it shouldn't be highest shell. Should be highest subshell, which I'll have to replace that code. So this should be a subshell. This should be a shell. This should be a subshell. And there we go. And now over here. Or over here. Over here. Over here. We will need back this one in range maximum and basically go forward. That should be it. Should be it. Hopefully. Subshells. This. That. Why is the length? Why is length there actually? Because I pasted it in the completely wrong place. H shell. There it is. This. Final string, this one. 2 will be shells, because I did it wrong last time. And subshells will be 1. There we go. I want to say that I'm like a genius, but because I did write this code, but you know, I'm an idiot, but a very smart one. I managed to read my own code, which is impressive. Please just walk, alright? Because it would be so much easier if you could just walk. Only 10 more. 5 more. 2, 1, 0. Yes. Let's see. This selection. They are non-existent. Why are they non-existent? They're not here. Why are they non-existent? Please tell me there's like a simple solution to this. There's actually an error on this line. There's an error in this line. Was not closed. It very much was. Wait, let me just take this and just print it every single time. How about that? It's not printing even. Which, because I'm doing walk thing, not fast. Makes sense. It's not closed properly. Alright, purple bracket. Looking for a purple closing bracket. There's a yellow closing one over here. We're looking for purple closing one. Oh, range, so above the green one. Above the green closing one, there should be also a closing. Excuse me? There, this. Should fix it. I fix. There we go. Simple. It could be. As an empty, I will get really mad soon. Maximum has which happens twice in here. I'm guessing the one that I don't know which one actually. In range subshells. Filtered out all the nuns. Let me just get this in here. Long lines. They are unusable. Yeah, we'll have to take this away. There we go. In range. Okay, so this is in range red, so up to this point, that's this range. Then we should have a closing this bracket, then we should have a closing this one, then we should have a closing this one, then we should have a closing this one. Or maybe you shouldn't, maybe we should not. Generator object gen is cool. We are getting code again. With the, why? Just because we didn't list it. Oh, is that the issue? That might be an issue. Can I please go down one? Thank you. That might be the issue actually, because that would make sense. Filter object. List filter. Where's not filter? Not filters over here. There should be a list. It's fine. It's fine. In range max filter. No, there's just filter in there. There's nothing else. Wait, why won't I just let this run actually if this works? That's a good question which I actually haven't thought about. That's... Huh. I should just let this run. To be fair, it's slow. It's very slow. It's horribly slow, but you know, works. I think. I hope. If it doesn't, I'll just give up. I really like that how the further we go in, the slower it gets, you know, to really show that. But alright. Saves to the table. There are no... Wait, there's no EC here. EC, that's what... How? Why is there no EC? What happened? EC is supposed to be this. EC is something everywhere. It's not. It's fine because I set it over here to something. It's yeah. I just undid all the progress. That doesn't matter. It doesn't matter. Let's try it again. This is very intense. Watch it simulate. Well, not simulating. Calculate everything every single time. It's nerve-wracking, to say the least. And quite intense, to say the most. I'm out of coffee for the last hour, so I think, I know, my brain counts time weirdly when it's under influence of any sort of psychoactive thing. Alright. That seems correct. That does seem correct. Look at this. 1s2, 1s2, 1p6, 2s2, 2p6, 3p2, 3s6, 3d10, 4s2, 4p6, 4d10, 4f14, 5s2, 5s6, 5p6, 5d10, 5f11, 6s2, 6p6, 7s2. And that's Einsteinium. No, smart element. Element of surprise. Alright, and over here we have to add, because I don't think we have it in the helium. There we go. This should be a 2. Cool, we have a table then. It's too early to give up, right? Yeah, it is. Great. Now all we have to do is just try something with it. Try to simulate some bonds. Let's first option is equal to input the atomic. That would be the first one. Now, if option is equal to the atomic, then, because for now, let's just simulate every diatomic bond, how it checks out. Yeah, we'll have basically different options. Diatomic is the simplest one, which basically means two atoms, that's it. How they bond together. This should be very simple, because the way it will work is we'll basically... This is the... Okay, it won't be pretty simple. It will be the simplest, but still pretty complex. Because the way we'll have to do it will be hard. So, the table, what's the structure of the table? Well, table structure is simple. It's an array. Array EC, that's mostly what we care about. EC and symbol. So basic gen. For first atom, first element in contents, for second element in contents, we do what? Well, first of all, we should save the results. So we just results, and also passing. Let's also have that as a thing. Move, yeah, passing, and in the passing we'll have plus all the passes. Move, cool. Basic gen. So we will save the results into the results. Means like this, and over here we'll do basic gen with open results the atomic, right? Indent block. Oh yeah, because of this. Yeah, that's right. For now, let's just print, make it whatever. Cool. Dump, and over here we'll need molecules as an array, and basically dump molecules. Now, each molecule will need a structure, different kind. When it comes to the atomic molecules, there's actually 118 times 118 options, which basically that's how many we'll get. So that doesn't actually matter for now. What matters is that we get pass, fast, or whichever one of them, and it matters that we get this code template for ourselves, because it will be handy dandy indeed, and it will be the atomic template. Over here, molecules, append the atomic template. And now what will this template look like? Indent, oh yeah, because of this, that's right. No, you don't need that. What will the diatomic template look like? Well, we'll have first, which will be character, or actually symbol. Second, for now we're doing the simple, so symbol, and then we'll get For now, let's do it very, very simple actually. The simplest, some might even call it, which would be is stable, and it will be false from the start. Now what do we do? Well, now what we do is we have to check if it will be stable. How do we check it? Well, using the subshell idea, the subshell check, basically. So, this will be horrible. First E, in its EC, election configuration, we'll first have to take a look at the length. So, length of its election configuration, which will tell us the last shell. That's it, the last shell of this element. That's electron shell of this element. Now, -1 will give us a really nice way to put it, like this, and just like that, we get the last shell. In this last shell, we would like to check actually the length of the subshells. And now the fun begins, because if I am looking for a way to actually code it very nicely, because basically we have to check how many electrons are required in order to achieve a full subshell on this last valent shell. And if the other atom, after subtracting that amount of electrons, has a full shell, that means it's a bond. That's what it means. So, but that won't work because because that's not how electrons are situated. But we do have two equations, which is convenient for how electrons are situated. Electrons start from the lowest. Okay, so basically we will have an n, not non-local. There are two important things, n and l. N, which is the shell. Oh, give me a second. Alright, so here's the way we'll do it. N would be the shell number, L would be the subshell number, right? And we will basically have to code it in a way so that we will check how many electrons do we need to add to the atom in order to achieve a stable state, and then we will check if after the second atom gives that many electrons away, if that second atom will also have a stable state, and then we just get them together to work it out. And if they have it, that means it's probably stable. It's probably stable, probably. So festive, very much festive. This is horrible. This is diatomic. This is the simplest case. It's the simplest one. Alright. So first, for n in range, this is the number of shells that the first possesses. For L in range, Then we should we go for each subshell? Should we? We might. I'm trying to think of a better way to do it. I don't think there are many. So for L in range, and basically this livestream configuration N, and then just length of that length. And now that's why I wanted to pass it this way, because right now it's more convenient than looking for a string or whatever. And then what we do is basically we can print right now, and what we can print is just print this L, and this will tell us basic gen diatomic. There we go. This tells us this is a lot of loops, may I mention. A lot of loops, and because of that, it's going through all of them. It's difficult to make out everything, but this basically tells us the amount of electrons on each subshell. Now, over here, by the way, let's also print after each of this. Print contents. Actually, won't as much. But so this gives us the electron of each. That's cool. That's neat. Now, how do we get it the correct way? So, what we need is we need to check the electron numbers in comparison to the ideal one. We could create an array of arrays in which we would save the number of electrons missing in each subshell. Yes, exactly. We could do that. That seems fine. So basically, in order to do it, why is this such a mess? It's chemistry, that's why. We could save that and we could then compare each of them. Okay, let's algorithmically think about something different for now, because this is the way it works, basically. We have 2n squared, this is number of electrons on shell, each shell. And we have 4l plus 2, which is electrons on a sub shell. Now, the way it goes is it goes n plus l, incrementing. That's how it basically goes up and up and up, which means we will need to start at 1, which would be first, so n and then l. Step by step, we have. Okay, let's just create a table of how it goes step by step. N and L. We have the first shell and the 0th subshell. Then we have the second shell, 0th subshell, and then second shell, first subshell. Then we have gives us 1, 2. Here we will have the total, which would be 1, 2, 3. Then we have the third shell, 0th subshell, which is also 3, but we first start with this one because it has lower n. Then we have a 3, 1, which gives us a 4. Then we have a 3, 2, which gives us a 5. But then we have a 4. Wait, no. Over here we should have a 4, 0. I forgot about that. 4, 0, which gives us a 4. Then we have a 3, 2, which gives us a 5. Do we see a pattern anywhere? Because that would be convenient. That's kind of what I'm looking for. Well, I feel like this is too short for a pattern. 4, 3, 2. Then we'll have because there are only 3 shells. Each shell has the same amount of subshells, right? Or am I wrong? There go. How many subshells are in each shell chemistry? 4 subshells? Only? I don't think there are 4. I think there's more. I mean, it's yeah. So each shell is getting 1 more subshell. Make up the shell. Yeah. Okay. Makes sense. Cool. That's good to know. So then we have 3, 2. Then we have 4, 1, which also gives us a 5. Then we have 3, 3. No, 3, 2 is the last one. Yes. So then we have 4, 2, which gives us a 6. And then we have 6, 0, which also gives us a 6. Oh, we missed a 5. Fuck. That's bad. So then we actually have 5, 0, which gives us a 5. And then we have a 4, 2, which gives us a 6. And then we have a 5, 1, which also gives us a 6. And then only we have 6, 0, which gives us a 6. Festive, 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 festive. Any ideas for a pattern that we can use to program it algorithmically? Because I could just do it manually, but that's a bad idea. Because I could like check. Yeah, this is the order in which they are filling in. Makes sense. Certainly does make sense. I feel like my brain hurts too much. That's too much science for one day. Tomorrow we'll do more. Yeah, tomorrow we'll do more science. We did a bit for today. I would like to see how it looks actually. This is what a single. This not that impressive actually. Not that impressive. Not that impressive at all. Because I feel like this is a very simple thing. This is certainly simple. Certainly is. We just increment n when we are done incrementing L, and if L plus n is small, there is definitely a way to do it. I'm just an idiot right now. We basically need a separate variable to increment it. Yeah, you know what, that'll be it for this stream. I just so tired. So that'll be it. I'm off to make more videos. Obviously, it's not the end of the day for me. And yeah, next time I'll try to finish the algorithm. Because it feels like such a simple problem, and if I cannot solve it, that means I'm really. Yeah, I need a break. So yeah, that'll be it. Thank you everyone so much for watching, and have a great day. Bye.